Section 8.1, graphing f of x equals ax squared. We are starting to look at functions besides lines, specifically quadratic functions, which is a nonlinear function of degree 2. Degree 2 meaning that my equation will have an exponent of 2. That'll be the largest exponent. And it has the standard form equation, y equals ax squared plus bx plus c. So just like for a line, it's y equals mx plus b. For a quadratic function, it's y equals ax squared plus bx plus c. And instead of a line, what we have is a parabola. That's a specific name for this curve here. It's a U-shaped graph of a quadratic function. You can see I have a point identified down here, point A. That's called the vertex. And this dashed line through the middle, you'll notice there's symmetry on either side of this. That's actually called the axis of symmetry. We'll talk a little bit more about that later on. Okay, so if I'm given the equation of y equals ax squared, in this case I'm given 2, g of x equals 2x squared, or h of x equals 1/3 x squared, I can graph them using t-charts or tables. And for this, sometimes for lines we're satisfied with 3 points. With parabolas, ideally we'd have 5 or more. And so that's what we're going to look at. I'm always going to start with, for these problems, 0. 0 is going to be right in the middle. It's going to be the most convenient one that I can pick. So for both of these, I'm going to start with 0. Now when I plug in, I'm finding g of 0. I do 0 squared, which is 0, times 2, which is 0. Same thing's going to happen when I do for h of x. 0 squared, 0 times 1/3 is, in fact, 0. So then what I have left is I got to figure out what other points I want to plug in. Now for g of x, I've got 2x squared. I'm just going to pick easy things here. I'm going to pick 1 and 2 going to the right, and I'll just pick the kind of the mirror image there, -1 and -2. And now I'm just going to plug in. So I'll plug in one at a time. When I first plug in 1, into here, I do 1 squared is 1, times 2 is 2. When I plug in 2, I get 2 squared is 4, times 2 is 8. And when I do the negatives, what actually is going to happen, or should happen, is I should actually repeat my answers because there's some symmetry here. And what happens is, remember, you're plugging in a negative and squaring that. That makes it positive. So -1 squared is +1 times 2 is 2. Same type of thing with -2 squared is +4, and doubling that gives me 8. So I can plot those 5 locations as points. I can plot the point 0, 0. I can plot the point 1, 2. I can plot the point 2, 8. And the other points as well, -1, 2, and -2, 8. And I get those 5 points. I'm going to connect them. I'm going to try to make this as smooth a curve as possible, and it's not always super easy. You just try your best here, and you try to turn nicely and connect through those. It's going to go on forever, so I'm going to put little arrows on the end there. And you see what I have. I have a parabola, but it's a little bit skinnier than the parabola that's already drawn there. The parabola that's drawn there is just y equals x squared. And so 2x squared is a little bit skinnier, a little bit more narrow. So let's see, looking at the next one, graphing h of x equals 1/3 x squared, because I'm going to square something and then multiply by 1/3, I'm actually going to be better off if I use multiples of 3 to kind of cancel out my denominator. Otherwise, I'm going to have fractions, which isn't terrible, but since we get the choice, let's pick some multiples of 3, like 3 and 6, and -3 and -6. Now when I plug 3 in, 3 squared is 9, times 1/3 is 3. And 6 squared is 36, times 1/3 is 12. And we'll do the same thing with the negatives, but the same thing's going to happen like it did before, and we're going to get +3 and +12. I don't want a negative there. And now I'm going to plot all those points. So I still have 0, 0, and the point 3, 3, and -3, 3. And you see that actually on my graph I've run out of space. I don't actually have room to go all the way up to 12. It would be somewhere around here, or somewhere around here. That's okay. We've got the 3 points. We'll connect them, make a nice curve, and we'll see what happens here. Connect these 3 points, or at least as close as possible, and so I get that. So that's my h of x, and I already had my g of x on the inside. And so the h of x there is a lot wider than the original parabola, and that's because this was a fraction here. Anytime that your coefficient is a fraction that's less than 1, or negative between 0 and negative 1, it's going to make it wider. Meanwhile, a larger coefficient is going to make it skinnier. So there you go. I hope that makes sense. Okay, so we probably notice a pretty obvious change here. The parabola is opening down. Well, that's because that's the graph of y equals negative x squared. If our coefficient of x squared is negative, it's going to open down. So what we need to do is we need to figure out what happens with the negative 1.5 x squared or negative 1/2 x squared. Well, I might want to think about negative 1.5 as a fraction, which would be negative 3 over 2. If I think about it that way, I realize that both of my coefficients are fractions with the denominator of 2, so what I'm probably going to look to use is multiples of 2 when I go around 0. So I'm going to have 2 and 4, and negative 2 and negative 4, and 2 and 4, negative 2, negative 4. Now we plug in. Now just be careful here, because when we plug in, we're squaring the number and then we're multiplying by negative 1.5. So the zeros are obvious. I'll spot you those. But go ahead and try to plug in, pause the video, and figure out the missing 8 coordinates from both graphs, and then come back and check your work. All right, how did you do? So take a look there, and we've got those coordinates. We can see that we're probably not going to be able to graph 4, negative 24, and negative 4, negative 24, but that's okay. So let's plot our points here. We obviously have 0, 0, and 2, negative 6, and negative 2, negative 6. So if I connect these 3 points, again, trying to have a smooth curve so that it turns nicely. We don't want to make it a sharp V. And there we have that. That's our first one. That's our g of x. And 1.5 is bigger than 1, so that's what makes it a little bit more narrow. Even though it's negative, that just means that it's going to open down. When I use the 1/2, the negative 1/2, I plot those points, still 0, 0. I've got 2, negative 2, negative 2, negative 2, and 4, negative 8, negative 4, negative 8. So I actually have all 5 of those points that I can connect. So I'll go through, and, don't need to be an artist here, just to do your best. And you see that that's a little bit wider than the negative x squared. 1/2 is a fraction that's less than 1, so it makes the graph wider. And there you go. So just a quick summary, what type of number a is really has an effect on the graph of y equals ax squared. If I just have a is 1, kind of the most basic, y equals x squared, it's this blue graph right here, y equals x squared. Now, if a is positive, like 0.25 x squared, or 4x squared, it's going to open up. All right, no matter what a is, if it's positive, it opens up. If a is negative, like negative 0.25 or negative 1/4 x squared, negative 1x squared, negative 4x squared, they're all opening down. A is positive, it opens up, like a smile, yay. A is negative, oh, it's a frown, it's sad, so it's negative if it opens down. And that's what we have. So then the other thing is, what type of number is A? Well, if A is a number between 0 and 1, when you make it positive, so this, don't worry about positive or negative, just think about it being positive, that's why I'm using absolute values here. If it's a fraction or a decimal less than 1, it's going to get wider, like the 0.25 or the negative 0.25 there. Meanwhile, if it's a number bigger than 1, again, thinking about it just as positive, that's why I'm using absolute value, then it gets narrower, it gets more skinny. 4x squared, negative 4x squared. In fact, the bigger the number, the taller and skinnier it looks. If you had y equals 50x squared, it would be this really, really tight thing right in here, really tough to even see. If you had y is 0.000000001x squared, we're talking something very wide. It almost would start to flatten out and look like a line, although it would be a parabola. And that's what it is. That's what really matters here. So that's what's important. That's how you can tell what your graph should look like. So I just want to take a second to look at maybe something that we could see these graphs coming in handy for. The arch support of a bridge can be modeled by the function f of x equals negative 0.0012x squared, where x and f of x are measured in feet. And you want to find the height and width of the arch. Now, because this coefficient of x squared is negative, we know the arch is going to open down, as we can see that it does here. This is arch is a parabola that opens down. And because this is a very small decimal, it's going to be a very, very wide parabola. And you can see it's much wider than it is tall here. And so that's just something we can look at and kind of compare the graph with what we would expect. Now, the height of the arch, we can see that just by focusing on a certain part of the graph here. You can see that it's going to go all the way down to here is where it stops. That's at negative 300 based on our scale, and goes up to the origin at 0. So that's a distance of 300. So the height of the arch is 300 feet. Meanwhile, the width, we'd expect it to be pretty wide here. Goes all the way from, it appears, 500 all the way back to negative 500 back here. And so that's a total distance of 1,000 feet. And there's a couple of different ways you could go about figuring that out, but it's easiest just to look at the graph and do some counting. So that's just one way that we can use this knowledge to kind of connect it to something that's in the real world. All right, hope this makes sense.